Hi, welcome to Algebra 2 Common Core. Today we're going to work on reviewing factoring techniques that you learned back in Algebra 1. So the first factoring technique, and by far the easiest, is called factoring by the greatest common factor. When we look at exercise number 1, we are given all binomials, and we want to find the greatest common factor. In each of the examples in exercise 1, the GCF, greatest common factor, is just an integer. So for example, in part A, 5x plus 10 can be written in factored form by factoring a 5 out of both terms in the binomial, and we would multiply 5 times x plus 2. So what we've written down is the factored form of this binomial. In part B, we want to factor out a 2, which is the greatest common factor, and we're left with x minus 3. In part C, we're going to see that the largest number that can be factored out of both of those terms is a 3. So when I factor out a 3, I have to remember to divide each term by 3. So 6x divided by 3 is 2x. 15 divided by 3 is plus 5. Remember that we can always check our answer by applying the distributive property. So if we distribute 3 times 2x, we do get 6x. And if we distribute 3 times 5, we do get 15. For part D, this one's written in a different order, but don't let it affect you at all. We can take out a 2 here, and we're left with 3 minus 7x. Now in exercise number 2, we're given binomials where the greatest common factor is not necessarily going to be just an integer. So for example, in A, not only can I take out the greatest common factor of 3, there's also an x common to both of them. So I'm going to factor out a 3x, and I'm going to be left with x plus 2. And again, reapply the distributive property to see that we do get 3x squared plus 6x when we redistribute. In part B, I'm thinking that the greatest common factor is a 5x, so I'm going to divide each of these terms in the binomial by 5x. So I have 4 minus x inside parentheses. For part C, my greatest common factor is going to be 5x. When I divide both terms by 5x, I'm left with 2x plus 5. Now, whenever I look at the binomial that's left, I should notice that there's no greatest common factor between the two terms that are left inside the parentheses. If there is still a greatest common factor, that means that I didn't take the greatest common factor out in the first step. So I'll have to go back and adjust. Please try part D on your own and come back and check your answer. In this example, our greatest common factor was just 10, so when we divided each term by 10, we were left with 3x squared minus 2. Make sure in all cases when you're factoring by greatest common factor that you always write down the greatest common factor in your final answer, in your factored form. Now in exercise number 3, we see that we're given trinomials instead of binomials. We're not going to do anything any differently. We're just going to look for the greatest common factor throughout all 3 terms. So in part A, my greatest common factor is a 2. I factor that 2 out, and I'm left with x squared plus 4x plus 5. Now we're going to see in a day or two how we're going to factor that trinomial, but for today we're only doing the greatest common factor on this one. For part B, we see that the greatest common factor is going to be a 5. So I'm going to divide each term by 5. So I'm going to have 2x squared minus 4x. Now be careful in this last case. Positive 5 divided by 5 gives me a positive 1. So make sure inside your parentheses you're still left with a trinomial if you began with a trinomial. In part C, we're going to take out a 4 and also an x, because I see that 4x is common to all 3 terms. Divide each by 4x, so I'm left with 2x squared minus 3x plus 5. And lastly, in part D, I again see that I can factor an x out of all 3 terms, and I can factor a 3 out as well. So 3x is my greatest common factor. I'm left with 2x squared plus 5x minus 7. The second kind of factoring that we're going to practice today is called the difference of perfect squares. We're always going to be starting with a binomial in this case. It's based on our conjugate pairs. So if I multiply together x minus a times x plus a, I'll get a product that's equal to x squared minus a squared. So let's recognize each of the binomials in exercise 4 as binomials that are the difference of two perfect squares. So for example, x squared minus 9. X squared is a perfect square, 9 is a perfect square, and I see that I have subtraction in between. So I can factor this as x plus 3 times x minus 3. Now in order to check this, you would have to use double distribution or FOIL to remultiply it out. So let's just look at one case of that. X times x does give me x squared. The outer terms, negative 3x. The inner terms, positive 3x. Those two cancel. And then finishing off, positive 3 times negative 3 gives us that negative 9. Now let's try the next one. In B, I've got 4 minus x squared. Both of those terms are perfect squares, and I've got subtraction in between. Now when we factor this, make sure that you don't put the factored form out of order. Since the 4 comes first, I've got to put the 2 first inside the parentheses. One will be a 2 plus x, the other will be a 2 minus x. For part C, I again see that 4x squared minus 25 are both perfect squares. So this is going to be the difference of two perfect squares. 2x times 2x gives me 4x squared. Minus 25 is going to be a positive 5 and a negative 5. And it doesn't matter which parentheses I put the positive 5 in and which one the negative. For the next one, again, I have the difference of two perfect squares, so I'm going to factor this into 4 plus 9x multiplied by 4 minus 9x. Now, we can introduce some fractions as well into these kinds of factoring because sometimes fractions are perfect squares. So for part E, x squared minus 1/4 is going to give me an x plus 1/2 times x minus 1/2. 1/4 is the perfect square of 1/2. For F, 25 minus x squared over 9, I of course know that I'm going to say 25 is 5 times 5. X squared over 9 is a perfect square, it's just x over 3 squared. So I'm going to say 5 plus x over 3, 5 minus x over 3. For part G, again I've got two perfect squares, so I'm going to factor them into the sum and the difference of their square roots. 4 over 81 is 2/9, but because that's in front of the x squared, I've got to say 2/9 x in both parentheses. For the negative 49 over 9, again that's a perfect square, so I'm going to make one of them plus 7/3 and the other one minus 7/3. Finishing it off with H, again I've got two perfect squares, so 36x squared is going to be a 6x times a 6x. 49y squared is going to be 7y times 7y. One will be plus, the other minus. Sometimes it's going to be necessary to combine several factoring techniques, so we're going to be completely factoring. Complete factoring means that we are factoring an expression until it cannot be factored anymore. If possible, we always want to do the greatest common factor first. So in exercise number 5, we're going to use a combination of greatest common factor and difference of two perfect squares to write each of the following in completely factored form. So for part A, we see that 5x squared minus 20 has a common factor of 5. So I'm going to factor the 5 from both of these terms. So that gives me 5 times x squared minus 4. Now, of course, I notice that x squared minus 4 is then the difference of two perfect squares. So I'm going to take one additional step and factor the difference of two perfect squares as x plus 2 times x minus 2. Make sure when you do this factoring, you keep that greatest common factor of 5 in your final answer. For part B, these two have a greatest common factor of 7, so I'm going to factor out a 7, and I'm left with 4x squared minus 1. I'm going to go down a little bit so I have room. So 7, because 4x squared minus 1 is the difference of two perfect squares, I'm going to factor that into 2x times 2x. 1 is also a perfect square, so plus 1 and minus 1. So my final answer is 7 times 2x plus 1 times 2x minus 1. In example C, I've got 40 minus 250 x squared. So for this one, I see that I can factor a 10 as my greatest common factor out, and I'll be left with 4 minus 25x squared. But of course, 4 minus 25x squared is again the difference of two perfect squares. So I'm going to factor that into 2 plus 5x times 2 minus 5x. Take a minute and try exercise D and come back and check your answer. Check your answer with mine. Did you notice that the greatest common factor was 3x, so I factored a 3x out? But then I was left with x squared minus 16, which is the difference of two perfect squares, leaving me with x plus 4 times x minus 4. The last kind of practice factoring that we're going to do is called factoring by grouping. Again, you were introduced to this in Algebra 1, but I want to show you two different techniques for doing factoring by grouping. Very often, factoring by grouping is applied when we have 4 terms in my original polynomial. So for example, in exercise 6a, I have x cubed plus 2x squared minus 8x minus 16. So one way of factoring this is to group together the first two terms and group together the last two terms. So I'm going to put parentheses around the first two terms and parentheses around the last two terms. I'm going to insert a plus between the two so that it doesn't look like I'm multiplying these parentheses together. My next step is to look for the greatest common factor in the first parentheses. So the greatest common factor is x squared. I'll take out that x squared just from the first two terms, and that leaves me with x plus 2. Now I move to the second group, negative 8x minus 16. The greatest common factor there is negative 8, so I'm going to factor a negative 8 out of both of those terms, and I'm left with x plus 2 as well. So these x plus 2's are actually common binomial factors. So I'm then going to factor x plus 2 out of each group. What am I left with in the first situation when I factor out an x plus 2? I'm left with x squared, so I put that in my second parentheses. In the second group, when I factored out the x plus 2, I was left with negative 8. So I'm going to go ahead and put a negative 8 with that in my second parentheses. Of course, we can go back and check this by double distribution. So I'm going to take my x and multiply it by x squared, and that gives me x cubed. Then I'm going to take the x, and I'm going to multiply it by the negative 8, so that gives me negative 8x. Then I'm going to take the 2 and multiply it by the x squared, so that gives me plus 2x squared. And then I'm going to take the 2 and multiply it by negative 8, and that gives me negative 16. So my check for this, while I've got to rewrite it in a different order, it does give me back my original polynomial that had 4 terms. So I know that in factored form, this polynomial looks like x plus 2 times x squared minus 8. Now, this was probably the method that you were introduced to in Algebra 1. So in the second example, I'd like to introduce you to what we call the box method. Any polynomial that has 4 terms and is going to be done by grouping can either be done by grouping or the box method, because the box method is just a different way of writing grouping. What do I mean by the box method? I'm going to make a box that has 4 squares inside. I'm going to insert each term into its own box. So 2x cubed minus 6x squared plus 5x minus 15. Now I'm going to look at the first row, 2x cubed minus 6x squared, and I'm going to look for the greatest common factor in that row. 2x squared is common to both. So I'm going to pull out that 2x squared. Then I'm going to move on to my next row. In the next row, I see that I have 5x minus 15. So what's common to both of those terms? 5. Now I need to approach the columns. Looking at the first column, 2x cubed plus 5x, that has an x common to both, and that's all. And then in the second column, common to both would be a negative 3. In this method, whenever the first term in a row or a column is negative, that's always going to mean that I'm going to factor out a negative. I then look at my answers by making this one binomial and this the other binomial. So in factored form, this would be 2x squared plus 5 multiplied by x minus 3. And you see that it's a nice easy way of coming up with my factored form by using a box. Now we've got 2 you try it problems here. What I'd like you to do is try one using the parentheses and one using the box method and decide which way you like better. We're going to be using both methods as we keep going in this unit, so you need some practice with both of them. When you're done, come back and check. I'm going to show both problems both ways. I've shown both of the examples using the grouping method and also the box method. So with number 1, I grouped together the first 2 terms and the last 2 terms. In the case of the first 2 terms, I pulled out a greatest common factor of x squared, so I was left with x minus 4. In the second group, I took out a 7 and was left with x minus 4 as well. So when the 2 parentheses match, I'm going to pull that out as a greatest common factor. It's a greatest common binomial factor. And then I'm going to multiply by the leftovers, x squared plus 7. Using the box method, I put each term inside its own box. And then I looked for the common factor in the first row. That gave me an x squared. Common factor in the second row, that gave me a 7. Common factor in the first column, that's an x. Common factor in the second column, minus 4. So you see that I get exactly the same answer. Go ahead and take a look at exercise number 2, in which case the answers x plus 5 times 3x squared plus 2 are exactly the same whether I've used grouping or the box method. We'll practice a lot more factoring in class. Have a great night, and we'll see you next time.